Hi, welcome to this lecture on GPU architectures and program. In the last lecture, we have been providing you with an introduction on how GPU memory access is managed and what is the impact of the way in which GPU memory is accessed with respect to performance of your program, and how these performance factors change with different variants possible for access expressions inside your program. And but of course, whenever we are talking about performance, you need a metric through which you can actually measure the performance of your program. So even if my metric is the execution time, how do I really measure the execution time of a GPU program? For measuring execution time of programs, one standard way is to profile the execution of a program. So what is profiling of a program? Essentially, there are profiling softwares through which you can monitor the execution. That means it will simply monitor some hardware counters present in your architecture, through which it can actually timestamp the execution of the program. And the typical way to do that is also, I can use a different profiler for profiling the execution of my program, or in modern programming languages itself, they provide with lot of profiling primitives. So I don't need a separate profiler, but just I can gather the times the execution time instance of different segments of a program and use which will essentially make use of the hardware performance counters present in the architecture. So these programming primitives will actually tell me when some part of the program actually started and when some part of the program actually ended, and by just measuring the difference and all that, I can simply point out what is the exact execution time for that segment of the code for that architecture. Now of course, we can see that this is an important scenario, because finally we want efficient code to be delivered, and the efficiency of the code is a function of lot of things in terms of what is the memory architecture design of the system, how many threads are executing, what is the global memory transaction width, and all the parameters we have discussed earlier. So let's first figure out how a CUDA program can be profiled using programming primitives. So in CUDA, the Event API provides you with the profiling primitives, and there are several types of CUDA events. They are all available under this type CUDA event _t. Now events can be created using a function CUDA event create, and created events can be destroyed from its scope. I can just destroy the event using the other function CUDA event destroy. Now these event variables can be used for recording timestamps using another primitive known as CUDA event record. Now of course, the difference between these recorded times I need to gather. For that, again, there is an API function which is called CUDA event elapsed time. So we will just see some example program where these things are being put into good use. So consider the offset access example program that we looked into earlier. Just to remember what it really was, let me just walk back to that earlier program on offset access. So this was our program. We are trying to run this small piece of code with an offset parameter s. So all we want to do is I want to check what is the execution time of this kernel on some specific GPU, and from our knowledge here, we have understood that if I keep on changing the value of s, definitely the performance is going to change. I mean, depending on whether I am doing offset access, there should be some pattern of change in the performance. Whether I am doing staggered access, which is the other variant of the program, so this is staggered access, there would be some other kind of impact on the performance. We want to see that how such things can really be measured. So as we have discussed, this CUDA event API is providing me with these functions CUDA event create, destroy, and event record, and finally I can measure the elapsed time using the CUDA event elapsed time function. So let us now have a look into the sample program here. So the first thing we are doing is we are defining two variables whose type is CUDA event t. The variables are start event and stop event, and I am going to use them to record timings at two different instances. I mean, of course, the start and the end time. So here we are writing a small driver program for the host side. So essentially a for loop through which the thing that I do is I am so the loop is going to run for these many times. In every iteration of the loop, what am I really doing is I am putting in the CUDA event record. So what is that? If you look into our earlier instances, that this CUDA event record function can be called to make one of the CUDA event types variables to start recording the timestamp, right? That's all we have done. So we have defined these two CUDA event type variables, and using the CUDA event record primitive, I am starting to record the execution time from this time point. Immediately after this starting point for recording, I am launching the kernel offset access with the parameters n. So essentially I am launching n number of threads, and it's being divided into n by block size number of blocks, and each block is containing block size number of threads. So the offset access code is being launched, and it is being passed with these parameters dA and I. Now if you look into the earlier code of offset access, so this second parameter is essentially the offset value. Yeah, so this is the offset access code and this is the offset value. So in this function, I am going to launch this kernel for each multiple number of times inside the loop. In every iteration, I am changing the offset value. So essentially, I am trying to launch this function multiple times, each time with a different offset. Immediately after the kernel's execution finishes and the GPU is notifying the host that it has finished, I have this CUDA event record with the stop event. So this function CUDA event record will start recording the timing with the stop event. That means essentially from this time I am measuring that when this counter is providing me the time point for when the kernel is going to finish, right? And then I would need a CUDA event synchronize for the stop event, because essentially these are all asynchronous calls, and finally I need to synchronize at this point. So essentially using the start event monitor, I have started the recording of time at this point. Using the stop event monitor, that is a CUDA event, I have started recording the time from this point. So essentially for these two, now if I provide these two different monitors to the other call CUDA event elapse time, now of course I can see that they are doing monitoring from starting from two different points. They are doing the event recording from these two points. This function, if provided with these two event monitors which have been recording all the events starting from these two time points, this function will actually go through them, whatever is there in their statistics, because they are doing a recording of the events that have been going on from different start times. So this function will take care of those differences in start times and record that difference in the in the first argument variable, right? So I hope the point is clear. I can use this data structure to monitor several kind of architectural phenomena, but in this case I am only interested in the difference in the start time of these recorders. That specific information can be provided to me by using this function, which is doing the work of actually looking into the recording events and their corresponding start times for these two monitors and providing me just with whatever I am interested in, which is the total elapsed time between the kernel launch and the kernel's execution finish. Now the similar thing I can also do for a staggered access. So when I do, so I will just change the code from offset access to staggered access. So one thing you have to take care that when I am talking about staggered access, this function call should also change to staggered. So that's some error in our part. As you can see, for staggered access, this is our kernel with S being the stride which is there. So I can do a similar thing for staggered access. So I just need to change this name So then, as you can see that using these two programs, we are able to figure out how the total execution time of the kernel changes with the change of the offset parameter and with the change of the stride parameter. If we plot this thing, so here we have a nice plot. So essentially we are changing the S parameter and we are trying to figure out that okay, what is the total memory bandwidth consumed by the system, essentially the elapsed time of the kernel when I am changing the stride of the kernel or I am changing the offset. We have got these two curves. Just take a minute to look minutely into these curves and figure out why they behave like the way they have been plotted. So let's first figure out what happens in the offset case. For that, let's first go back to the code of offset access. So this is how it is, right? So considering an offset of 1, you are getting first when you don't have any offset, for every execution of the kernel, you have one global memory read followed by one write. Consider an offset value of 1. So now you have two global memory reads and two global memory writes. What happens with an offset value of 2? So with offset value of 2, you will have the data points from A2 up to the data points in A9. And then you will have data points from A10 up to the data points up to A17. Then data points from A18 up to the data points A25, right? This is how things will go on. So essentially whether my offset value is 1 or 2 in both cases, the global memory reads will require 2 transactions followed by global memory writes requiring 2 transactions. With offset value 3, again I would have the same thing. So with offset value 3, I am accessing data, let us say from A11 up to A18. But again, what is the number of transactions? 2 global memory transactions for read and 2 global memory transactions for write. So in this way, as you can see that with the increase of S from 0 to 1, I have a bandwidth reduction. But after that, things remain same. With offset 2, 3, 4, things remain same. But what happens when the offset value is same as the warp width? So when S is 8, then what will happen is for warp 0, you instead of accessing from A0 to A7, you would be accessing A8 to A15, right? So again, everything is nicely coalesced. So you are back to global memory transaction 1 for read and one global memory transaction for write. So essentially, with respect to offset, what is the situation? When you have no offset for this program, you have the best performance. Whenever you have some offset, your performance decreases, but it decreases to the point which will remain constant for further increase in offset until the point where the offset is aligned with the warp width, so that again you have nice coalesced global memory transactions, and that will again increase the bandwidth. So now with this idea, if we go back and see that the total the performance reduces first, but that just for the first value from S0 to S1, and then this is all specific to that program. It remains the same. Then again, when it will get access, it will get byte line. So here we are doing all our runs on a Tesla K40 GPU, and of course, as we know that the standard warp is a 32 sized. So immediately at 32, things will be getting byte aligned nicely. The global memory is again nicely coalesced as the offset 0 case. So I have a reduction, but then the reduction doesn't change. I have just doubled up the usage. I mean, for all the threads for that specific program line. Then again the performance is back to what it was for 0 offset, right? but that is not such a case for strided, right? Let's go back to the strided code once again. So as you can see, when you are running the strided code, when your stride is 0, so there is no stride. So you have again for every instance of this operation, one global memory read and one global memory write. What happens with stride? So this is the stride is changing from 1 to 2 now. The number of global memory reads and writes have doubled up. With stride 4, the number of global memory reads and writes have further doubled up with respect to s equal to 4. So if I keep on increasing the stride factor, the global memory transaction, the number of transactions is doubling up, right? So this would actually lead to drastic reduction in the memory bandwidth provided by the DRAM to this kernel. So this will lead to huge performance loss, and if I look at the effective memory bandwidth that I am getting, it is reducing drastically. So the more I increase the stride, my memory accesses are getting even more scattered. So there will be at some point I will lose all kinds of coalescing, and in a worst case I will have for all thread IDs inside the warp I am doing separate global memory transactions, and that would be the worst case. So I hope that is understood, because nothing can be worse than that. I am executing a warp, the warp has 32 threads, each of the threads are requesting locations in the memory which are far apart, and they are so much apart that they cannot be brought in a single transaction. So that is the worst case, right? I mean, so after that if I go on increasing the stride, it really doesn't matter, because essentially then by that time when for each access I am doing a separate global memory transaction, that would mean for every warp, every instance of execution of the warp for some load or store instruction, I am going to do 32 separate global memory transactions. So that is the worst case performance, and that would give me the saturation point in this curve, the lower saturation point in this curve, right? Now, of course, I can use a better arrangement of data points for whatever computation I am doing to reduce the number of global memory access I need to do in such pathological cases. So overall the recommendation is that whenever you are writing your program, you need to make good use of your memory segments. You have to understand the GPU's memory hierarchy, and accordingly you should write the code so that the access patterns are nice with respect to coalescing. Now this is where the role of shared memory would come in, because as we all know that we have discussed earlier many times, that inside each SM you have a portion of the memory which can be configured as shared memory or L1 cache. If you can tune your algorithm and write the code in such a way that you are doing less number of global memory accesses, and by doing some smart usage of shared memory, that can increase the performance of your code drastically. So although in general the property of applications is that they typically require different threads to access the same data over and over again. So that's we know that the principle of locality or data reuse. I have a principle of locality which is spatial as well as temporal. So different threads may need access to the same data, or threads may need access to data points which are located in neighboring regions of the memory. So the primary thing is, since different threads would need access to the same data, if I keep the data in the memory, at some point some other thread will require the data. And also if I bring data in chunks, which is actually done by the wide transactions that we always do, the basic philosophy is that whenever you are bringing in data to the memory and you are bringing data in chunks, it may so happen that in future with a high probability you would be actually needing the nearby memory elements which are already available to you in the cache. So the shared memory can be configured as partly as a cache and shared memory, and the good thing about the shared memory is all the threads inside the block have a consistent view of the memory. So in many cases based on this idea that different threads can actually access to the same data over and over again at different time points, maybe I can reduce the global memory accesses by avoiding the multiple load and store from the global memory, but rather I put the data in the shared memory and keep it there for collaborative access by other threads at different points of time. So, I make one thread responsible for bringing the data and putting into the shared memory using a specific shared data type, and then that data point can be used by some other data point by some other thread by other threads at different points of their computation. Now, if this can be done, then as we can understand that every thread, whenever it is doing a memory reference, if it can get it from the shared memory, then there is an order of magnitude reduction in the access time with respect to the global memory access, and that is quite useful as an optimization. This is one of the primary motivations of keeping a shared memory segment in the GPU. It allows threads inside the block to collaborate among each other. The data elements brought in by threads in a block can be used by other threads in the block at different points of execution by accessing them from the shared memory, if they are actually made to be resident in the shared memory by the programmer. Now, this is something important. The hardware does not really decide what should be or should not be in the shared memory. The hardware decides this from the cache by using standard cache principles. I mean, using the cache's read and write policies, right? But for the shared memory access, it is the programmer who has to decide by giving suitable data types that which data point should be resident in the shared memory and which data point should not be resident in the shared memory. Now, looking further deeper into the shared memory. So, how is the shared memory structured? This is something we have discussed again. This is a small recap. So, each SM typically has 64 kilobytes of on-chip memory, which can be partitioned between the L1 cache and the shared memory. Now, the setting is typically like this, that you have 48 kilobyte out of the total 64 configured as shared memory and rest 16 kilobyte configured as L1 cache, but it can also be the reverse. By doing suitable programming setting, you can make it like 16 KB shared and 48 KB L1 cache. As I told earlier, that if it is L1 cache, then it is managed by the hardware just like the cache memory is managed. But if it is the shared memory, if it is defined as a shared memory, then the programmer has to manage it through suitable type definitions for the variables in the code. Now, this can be configured during the runtime API. I mean, which part of the the given memory block which is on chip in the SM, whether it should be a shared memory or how much of it should be shared memory and how much of it should be L1 cache. Essentially, you have only two options that can be that actually can be configured using the CUDA API. Now, suppose you want to configure it permanently from the host for all the kernels. So, a host can technically launch multiple kernels one after another asynchronously, but if I want a specific setting of shared memory and L1 cache available for all the kernels, I can do that using this function CUDA device set cache config. So, this is the function which will take care of doing the configuration of the shared memory. I mean, you can just look into the manuals online for NVIDIA and figure out what are the parameters for this. Or if I can also do it in a per kernel basis, that means I have a host code for one kernel, I can configure the shared memory and the L1 cache in one way, and then for the next kernel I can configure it in a different way. Of course, it depends on what is the property of the kernel, how many threads are getting launched, how the threads are being arranged, whether it is actually useful to have more shared memory or whether it is useful to have more amount of L1 cache. It depends on the programmer's perspective. He has to figure out whether having more shared memory actually helps that specific kernel. Then he would actually like to use this function to configure that memory segment with more amount of shared memory. Otherwise, depending on if you want fast access to decrease the latency and you don't have really control over what really would be used among the variables by which thread, you can actually have more amount of cache. Typically, the principle, before concluding here, I will also like to put in one important point which you have seen earlier, that GPUs typically have less amount of L1 cache with respect to CPUs. The primary reason is that since I am going, first of all, I have the shared memory, that's one segment that I have, so I can afford to have some L1 cache. But the other reason is that in this case, if I have smaller L1 cache, I am trying to hide the latency of the L1 cache miss by using more threads. So when I compare CPU computing and GPU computing, in CPU computing, although I have multi-core, multi-threaded CPU cores in a CPU, the number of threads executing parallelly in the CPU are much less with respect to GPU. So the objective is to execute the threads fast enough. One important impediment in terms of executing a thread fast enough is memory operation. So I have good motivation for using large caches, so that there is a high probability I can find whatever data is required in the L1 cache, and that would reduce the memory access penalty, and that will give me better performance. When I am using GPU, essentially what I am doing is I am using I am actually using lot of threads in parallel, right? I am launching more number of threads in parallel. So I really do not care if some of the threads are suffering due to non-availability of data in the L1 cache, because technically I have too many other threads to execute. I have many warps waiting. I have launched more number of warps than I have actually available physical SPs. So I can just stall that warp and execute some other warp whenever this warp is stalled due to some high latency operation. So this is how things are managed. There are different philosophies. Since in this case I have more number of threads to manage, if some threads are waiting due to non-availability of data, that is fine with me. So in this case I can afford to have smaller amount of L1 cache. So with this we like to end this lecture, and maybe in the next lecture we will like to see a good program example through which we show how the usage of shared memory can be a nice optimization with respect to performance. Thank you.